Welcome, everyone. Good morning, good afternoon, good evening from whichever time zone you are joining from. Thank you for joining us today for this exciting panel discussion in the semiconductor space. It's truly a pleasure to have each one of you here, and I trust you all are having a wonderful day till now. Today, we have a very interesting topic, which is semiconductor innovations in the digital era, shaping the future landscape. We will discuss in detail about the same throughout our webinar, but before that, let me begin by introducing myself and AI Core Spot as a platform to you. My name is Nitin Naveen. I'm Vice President Innovation Strategy at AI Core Spot. With over a couple of decades of experience in different consulting firms specializing in emerging technologies, I feel fortunate to consistently engage with global leaders, stakeholders, innovators, and all those who are driving the positive change. Joining me today, I have Arvind, and in the back end, I have Naveen, who will be infusing energy to in this event. A big applause for their dedication in making efforts to make this gathering a great one. Some facts about AI Core Spot, which I wanted to bring forward in this forum to all of you. It was founded over 3 years ago and is meant to be a source of inspiration in the tech landscape, focusing on different emerging technologies such as AI, ML, robotics, IoT, and much more. Our webinars serve as a platform to share the latest advancements in these fields, providing fresh insights every month as we continue to gain momentum. We aim to be the leading AI-driven community worldwide, fostering collaboration and growth among like-minded individuals like you. We are committed to curating industry-backed webinars and hybrid events, leveraging insights from industry thought leaders, subject matter experts, all our trusted partners to deliver credible and valuable content. Additionally, our content is also crafted across various digital platforms which we have, which includes videos, blogs, podcasts, and monthly newsletters to keep our audience informed and engaged. Bringing back the attention to today's webinar for which you have registered for, the topic is really exciting. As I told beginning the beginning, it's redefining possibilities, that is semiconductor innovations shaping the digital era. Gear yourself for an enlightening discussion on a lot of different things which we'll discuss throughout the webinar, like impact of miniaturization, concurrent design methodology, challenges, opportunities, and much more, which is creating excitement within the scope of semiconductor space. Our panel of experts is poised to share invaluable insights and engage in thought-provoking discussions that promises to leave a lasting impact. Before starting the conversation, we would like to extend gratitude to all our community partners. We have three great companies, which include Renesas Electronics, Infovision, and AMD. Their invaluable contributions have been instrumental in making today's webinar possible. And of course, a heartfelt thank to all of you attendees. Your presence and participation are deeply appreciated. As we embark on this journey together, our primary goal is to equip you with invaluable insights and facilitate meaningful connections. Whether you walk away with innovative ideas or some new connections, your engagement is a testament to our collective success. Without further delay, let's introduce our esteemed speakers for today's session one by one. First esteemed speaker is Sheila Pillai. Maybe have applause for her. She is Senior Director Engineering, Renesas High Performance Computing Automotive Division at Renesas Electronics. And our second esteemed speaker is Rakesh Anigundi. Maybe have applause for him as well. He's Director of Product Management at AMD. And third esteemed speaker and moderator for today's event is Vivek Parmar. Maybe have applause for him as well, as will be going to moderate this particular panel discussion. He's Chief Business Officer handling telecom, media, and technology space at Infovision. Before we begin, just a quick disclaimer. The views expressed by all the speakers are personal and not related of their affiliated organization which they represent for. So without wasting any time, let me hand over the stage to Vivek to begin this exciting panel discussion. Over to you, Vivek.
Thanks, Nitin. Wonderful to be here, and exciting panel discussion that we have at our hands. And thanks to the panel for making time for this discussion. Happy to be here. So semiconductor innovations have been pivotal in many ways in shaping the digital era, as I would say. It has kind of worked its way through various industries and in many ways has fundamentally altered the way we live, we work, and the way we communicate with each other. So ladies and gentlemen, welcome to our webinar on semiconductor innovations in the digital era. Today, we embark on a journey to explore what the transformative power of semiconductor has been and what has been their impact on the rapidly evolving digital landscape. We'll also peep a little into the future and see what semiconductor innovations hold for us in the future. Um, in this panel discussion, we'll delve into major trends that will define the future of the semiconductor industry, and some key takeaways which we see in the semiconductor advancements that is shaping the future landscape, including themes such as how the chips, etc., are becoming like smaller, more faster, and as Moore's law, which posits that the number of transistors on a microchip doubles approximately every 2 years, how that has been like a driving force behind the semiconductor innovation for decades now. As chips become smaller and more densely packed, with various transistors and all, they become faster, they become more powerful, and more energy efficient at the same time. And this trend continues to enable more advancements in computing power across various devices, from smartphones to supercomputers. Another important aspect of what we are hearing quite often nowadays is the whole AI and machine learning phenomenon rise. So the rise of AI and ML has been fueled by advancements in semiconductor technology. Specialized chips such as the GPUs and TPUs are designed to accelerate AI workloads in many ways, making tasks like image recognition, natural language processing, autonomous driving, for which Sheila has a lot of experience on, more efficient and accessible. Another trend that is shaping up is the whole high performance computing phenomenon. So the semiconductor industry has continually pushed the boundaries of computing power in many ways, enabling the development of very high performing computing systems in the field of scientific research, weather forecasting, financial modeling, and of course AI. Innovations in semiconductor material design and manufacturing processes have contributed to the creation of increasingly powerful processors and accelerators. Not only that, there is this recent phenomenon of quantum computing. While still in its infancy, quantum computing does have the potential to revolutionize fields such as cryptography, material sciences, and drug discovery, right? Another important aspect of things that is shaping up is the whole edge computing phenomena, right? So as the volume of data generated by all these connected devices continues to grow, there is a growing need for computing resources closer to the point of data generation. And edge computing, which now evolves and processes data locally on IoT devices or the network edge, relies on to a large extent on these low power, high performance semiconductor chips to deliver real time insights. One of the most important aspects of things that we are seeing overall, and not in just in the semiconductor industry, is the whole energy efficiency and how sustainability plays a role in this whole industry, right? So semiconductor companies are actively researching and developing energy efficient materials, designs, and manufacturing processes to reduce the environmental impact of electronics. We will touch upon a few of these technologies during the conversation today. What we're not going to touch upon is things like supply chain issues or geopolitical tensions. We'll just keep this discussion limited to technology initiatives. So our speakers will shed light on these trends and discuss how semiconductor innovations are shaping our digital future. So without much further ado, let's dive in and unlock the secrets of silicon. My first question, Sheila, is primarily directed to you and then to Rakesh also. With the whole point where I started, right? So smaller, faster, and more efficient, right? So what has been the impact of miniaturization on shaping up the telecom on the semiconductor industry? If you could shed some light on it, that'll be great.
Thank you. Thank you for having me in the panel, and I'm really excited to be part of this. And actually, with the industry moving towards more and more integration of accelerators like high-end GPUs, ALML engines, high performance, network interface, and more CPU cores, miniaturization has made these solutions possible, which otherwise would have been impossible or even economically feasible. And also, cloud computing requires another level of power and performance. So, which is driving the chiplet technologies. These days, if you see a package substrate look like a mini PCB, which is enabling to bring compact product to the market. And as you have said already, all these changes are possible because foundry technology is pushing the envelope, and the current trend is 2 nanometer, furthering the Moore's law, which many thought would have been died by now. So advancement in technologies like a gate-all-around transistors, 3D devices, power vias, and chip-level technologies is enabling or making miniaturization a reality. Another gain of miniaturization is for achieving low power and also getting better performance. And also you talked about the AI. AI has been there for a while and it has been a buzzword. But now AI solutions are possible because of the amount of integration that can be achieved. And AI needs a lot of computing and high memory bandwidth. And that requires this advancement technology because it can make these solutions possible. And this is a paradigm shift, and applications like self-driving is becoming a reality where a lot of AL and ML is required.
Thanks for that input, Sheila. Rakesh, anything from your side on this topic of miniaturization?
Yeah, I mean, you guys bring up a great point. Miniaturization, in fact, I would argue, has been driving the whole world economy and GDP. Semiconductors and silicon, which have been in 15 years, typically don't tend to get a credit for what it is enabling. So maybe I can make a few comments on that. Vivek, you made some great points about power efficiency it brings in. Sheila talked about what are the applications. If you take a step back, immense amount of technology goes in to fabricate these new transistors. We are packing in billions of transistors into a small device like a smartphone. And what does that mean to us, right? If you take a step back and I can realize that there's a gamut of different devices this powers, right? Smartphones, you talked about consumers. The smartphones are becoming thinner. The tablets are becoming thinner. We are having 15 megapixel of devices packed into the device. And the key enabler for this, yes, there needs to be a software which brings in all together, but the key enabler for this has to be the miniaturization and the advances that the semiconductor industry enables. I treat semiconductor industry as the bottom of the value chain, which enables these different devices and applications to come to bear.
Nice, nice. And picking up that cue from what you just mentioned, Arvind, so designing and manufacturing chips is a complex task. I mean, intuitively also it looks like a complex task, even if somebody doesn't know anything about manufacturing, right? And so how do you make it more predictable and guarantee quality? So can you tell me in some ways, some challenges that you may have faced or how you navigated through them and deployed a seamless SoC or IP design flow? Maybe Sheila or Rakesh, whoever wants to go first, maybe some thoughts on that aspect?
Rakesh, you want to go first?
Yeah, at a very high level, I think it's underrated on how complicated it is to put the whole SoC together, right? We are talking about not billions, we're talking about packing in multi-billions transistor into the same chip, right? It starts very well from definition of, hey, what kind of features is needed, what kind of IPs we need to integrate into the chip. It usually starts there. But one of the biggest challenges that we have, that I have personally faced is the design cycle from the concept of what features is needed into a particular chip to the time it goes to production. It can be anywhere from 6 months to 18 months, right? If you're leveraging an SoC, it's smaller. If you're building something up to ground up, it's more larger. And given the world we are in, the requirements keeps changing so often, right? Hey, maybe, we are very close to the definition. We have locked in the design. We are 2 months away from fabricating. We get some new market signals. Hey, we need more data speeds. We need more IO. That's a constant struggle on how do you keep this complicated design flow, which has been vetted across different flows. At the same time, how do we keep nimble? How do we keep adding more features to the whole design flow is one of the biggest challenge. I'm a product manager, and I'm not a great friend to all my engineers when I bring them last minute requests, but we need to be keeping up to pace with what changes that are happening in the market.
Yep. No product manager is a friend of engineering. But good point there. Sheila, any thoughts from your side?
Yeah, I think Rakesh touched most of the points. I also really want to reiterate that it's a complexity and complexity. Now, like SoC is just not like a CPU cores and some memory and other stuff. We just got a lot of other functions, ALML engines and other. Yeah, we are integrating more and more. recently I was talking about one of the SOC we are doing. I call it like a kitchen sink. There are so many things needed, and also at the same time, there is some level of market uncertainties. And because these products, it takes more than 2 years to get into mass production. So with the landscape, like Rakesh was telling, landscape can change, use cases can change. And so feature changes are inevitable. And I know when I was in other companies, product planning engineers come with some changes in the middle of the execution. I do tell you, cannot convert a PowerPoint into a system on a chip. You cannot keep on asking to change and keep the schedule. That is other one thing is customers need really more performance, low power, and also cost. So we had to optimize the chip maximum for a PPA. At the same time, schedule is sucking. So all this considering the complexity and also the time to market, everything is making the chip designs very, very challenging. Also, we need to squeeze every milliwatt of power, especially for high performance computing that runs in large compute farms, which takes a tremendous amount of power from the grid. So even a milliwatt of power optimizing can go a long way, because these chips are used repeatedly in farms, so you can get a large gain of power reduction in power consumption. And also, the other thing is these chips are, most of the chips are done concurrently. And concurrent design means the technology, IP development, SOC development all go in parallel. And I know when we were doing in the AMD, many years ago, when I was in AMD, we were moving away from a monolithic chip development to an IP SOC development flow. And there were a lot of challenges initially. Especially there are a lot of FUD concerns because people were concerned about the quality, concerns about the schedule, concerned about the deliverables, and also we were pushing this reusability, and also from the product planning and other folks. So how can you use a IP developed for one SOC can be used for multiple SOCs? So we, as a core leadership team, we had to meet several times, discuss, and come up with a plan how to navigate through that. And that is where we need to have very meticulously planned the technical requirement of handoff of IP, and also how do you close the loop and handshake at every stage with the next level of integration like subsystem or SOC. And also we had to put together a plan where meticulously plan this and put together some metrics and milestones so that we can track the progress and predictability. And as I said, these complex SOCs are done in a very globally distributed team because of the amount of staffing and resources required. And this has its own challenges. So I would say like communication. The transparent communication is very, very vital. And also we had to manage the development in a very tightly to make sure the quality is not dropped. And also we had to put a lot of checks and balance to make sure that no one is dropping the ball. And the other thing is having a holistic verification, because you were talking about there's so many IPs coming from different worlds. We'll have make or buy, some are coming done internally, some made from external vendors, and we are pulling it all together. So we had to make sure that it's verified in a holistic way, from all the way from a macro to a post-silicon subsystem, IP level subsystem, full chip, and emulation is playing another big key. So that is another big concern. I'm sorry, I'm going on and on, but emulation.
Good point.
Emulation. Because of the shift left design methodology everyone is adopting, emulation is playing a key role, and emulation has to start much early in the design. That is where the emulation team and the software team wants maturity of the design at a very early stage. And that is another impossible task, because unless you have the maturity of the design, we cannot run this emulation platform like Palladium and Zebu to run the software on it. All this add to the complexity and challenges and risk for the high performance computing, or whether it is automotive SOC during the development. And other one which Rakesh like said, most of the things are in advanced node. And that also creates its own challenges because PDKs are evolving. So we had to accommodate for the PDK changes and design for uncertainties, and some of the hard IPs had to design with added margin to actually accommodate uncertainties if the PDK changes by the time from a 0.1 or a 0.5 to 1.0. That's normally we tapered when the PDK is more mature state around 1.0.
Interesting.
I can go on and on, but I'm going to stop here. Otherwise, I'm going to take the whole session.
No. I know. Just for everybody's reference in the audience, so Sheila has developed and led both server and automotive SoCs, and both of them are very complex and challenging. So I think all this talk is coming from experience that she's had. So thanks a lot for that input and commentary there, Sheila. Moving on a little bit, I think there are some advanced packing methods, right? Overall, such as 3D integration and chiplet designs, which enhance the modularity and flexibility in the manufacturing process, right? So Rakesh, any thoughts on how they are kind of being implemented, and then what are the steps that go into it?
Yeah, I think, we should, I will definitely like to touch on that. But if you look at what are the driving forces, why do we need 3D chiplets? Why is there so much focus on 3D packaging, for example, right? We talked about how there are diverging market needs. Even if you take a small segment, a particular market, right? When you're servicing automotive, you're servicing in a smartphone, even inside that, there are divergent needs. A value chain smartphone has a different features than a high-end smartphone. You take PCs, right? A startup PC has a different performance, power requirements than a big PCs, right? And typically in all of these semiconductor companies, they would like to optimize stuff. They want to, have a bare minimum set of designs to service many different end markets. But at the same time, you want to package as many transistors as possible to power up all these amazing features, right? That's been the trend that the semiconductor industry and the semiconductor companies have to be faced with, right? We all know Moore's law was our friend. We were packaging more transistor every 18 months. It did address majority of the requirements about how do you pack in more power and performance. But now, if the question is, if you want to have the ideal solution is, hey, you have these technology nodes. You can choose based on your market design. Hey, for some, a 3 nanometer is fine, but some, you can go to 4 nanometer, 5 nanometer, or even 10 or 12 nanometers, right? There is a choice that exists in the technology node. And we know that Moore's law might not be, expediting in the same sense it has been. What do we need? We need ideal set. If you look at my son, you need a Lego bits, right? You have a Lego bits, you can put these Legos together, and then you can start servicing different markets without having to take the cost of retaping, multiple solutions for different market. That is where these concept about 3D packaging and chiplets, for example, becomes extremely interesting, right? You can have, for example, a die where you put more of your logic, like your CPUs, your GPUs. You can have a die where you're probably doing more custom circuits, which is designed for a specific workload, a specific target market. Then you can have a separate die, which is just doing IOs, right? IOs, they are very, to me, sometimes it creates a lot of nuisance because these IOs are changing, the speed requirements are changing, but you need to anticipate that and lock in your IO requirements well before on where the market needs is 2 to 3 years from now, right? So you can think about all of these that can be designed as the Lego pieces in a different die, and how do you put that together, right? That's where 3D packaging and having chiplets where you can stack these different chips, then voila, you have an SoC which can now have different feature set targeting different target markets, becomes extremely interesting, right? So as a concept, this chiplet and 3D packaging is very, very compelling, but we need to keep certain things in mind, right? It's not like a silver bullet that can satisfy all the needs. When you're talking about chiplets or when you're talking about 3D packaging, they do come with their own fixed cost, right? COGS, or even every Sheila will vouch for this. Every millimeter of a silicon die, there has to be a great business get pressure to grow your die, because that's directly impacts your bottom line. So a lot of the analysis that I've been involved that we typically do is these technologies are great. We want to imbibe them in most of our product stack, but there's also an analysis that needs to happen as to when some of these chiplets or when some of these 3D stacking technologies make sense to the end market. But I'm very positive about this. I do think this will spur an ecosystem and can democratize more of the silicon design. We always talk about open sourcing AI models, democratizing AI models, and having this open source community developing these great AI models, right? Which is great. And you see Llama 3 is a good example of that, which has spurred innovation. To me, this chiplet and packaging disparate dies is that open source for our semiconductor industry, where a customer in the future can take, hey, I have this best logic die from company A, best IO die from company B. I like this, domain-specific accelerator for company C. I'm just making this up, right? Then you put all of that together, then you have an optimized silicon solution for your end market. And companies inside can do the same. They can put all these Lego pieces together to start, addressing different market needs.
Very interesting. I think I learned something very new, Rakesh. I was not even aware of these techs that are shaping up. So thanks a lot for that commentary. Staying on that topic of manufacturing, Rakesh, you've been involved in all these coordinations with the.
I also want to add one point for chiplet. The main concern, because a long time ago when we were looking at in AMD also, we were debating a lot because of the chiplet. The yield is a big factor for the cost, and it is like a non-good die. That's what we said. The defects can be exponentially increased, and it can add to the cost because of multi-die. So that is something we need a lot more the quality for the design, and also a lot more testability, because to make sure that non-good die, because as and when we get to next level of integration of packaging, this can create quite a bit of loss and add to the cost of the chip developed in the overall operations and the COGS. So that is a very important thing we need to keep in mind. Chiplet, the non-good die is a main factor to make sure that we get a good packaged quality chip at the end of the day through chiplet.
Interesting. Nice. Right. So what I was alluding to earlier was Rakesh, in terms of the involvement of foundries and the consortia in reducing the overall development time and speed up the implementation of these semiconductor innovations, what are your thoughts on that, and what have you seen, or what are you seeing in the industry at this moment?
It's a very interesting problem that semiconductor industry need to come together to solve and look at this, right? If you look at different spectrums, what are at play? You have fabrication units, and you have different kind of players, right? You have TSMCs of the world, global foundries, Samsung. Each of them are great in different aspects. And Intel with their foundry services, there are a lot of different players in a foundry business, right? And it's not cheap. It's not cheap. It's not cheap to set up these fabrication units, different processes, and even the amount of technology that goes into creating these next-gen libraries and stuff. It is a very expensive affair, right? That's the set of players at one end of the spectrum, right? Then you have semiconductor companies. You have companies with varying, pockets, right? There are big semiconductor company, billions of turnovers. They have the luxury to engage with these fabrication units, advanced technology groups in each of these companies, right? Can engage and get a mutually beneficial output out of it, right? Through some kind of a financial engagement. We call that as pathfinding. Most of the semiconductor companies are invested in that. There will be a pathfinding group, basically informing the product group, the design groups on, hey, what are the technology nodes to choose? What is the performance to be expected, right? So that kind of a relationship between a foundry and a big semiconductor company, it's happening, and it's good to spur innovations and to guide the path for pathfinding issues forward, right? Then at the other end of the spectrum, you have universities, you have researchers, right, which don't have the same kind of deep pockets to be able to operate at the leading technology nodes. Or there can be even startups as well. I do have some experience working with semiconductor startups, right?
Right.
Fabricating or taping out your chip, it's not like a few $1,000,000. It is quite an expensive affair. And all of the startups might not have the deep pockets to fabricate it. And there might be a lot of research going on, right, in academia as to, hey, what materials to use, and how can we work with, newer kind of technologies. Like, there was a lot of these things, exploration about analog circuits. How can we make analog circuits fabrication more simpler? So this are the set of disparate players where I think, there are different standards from different companies. The big question is, how can these different players start working with these foundries, forming an alliance, be it in research, and keep pushing the boundaries of what is possible? I think there is a lot of opportunities, but the barrier to entry typically is this is an expensive affair. Just like a software startup, not any independent researcher, not any independent academia can leap forward and participate in this progress, right? That's been a struggle and a tussle in the semiconductor pathfinding world.
Interesting. Nice. Shifting gears, I think, how can I not touch upon the topic of AI? It's everywhere. And I think semiconductors themselves are playing a very pivotal role in how we are enabling AI in general, right? But in terms of the challenges one faces while developing these chips for high performance computing, and where is the world headed to in terms of these high performance computing chips, etc.? Do you have some thoughts, Rakesh and Sheila, on the aspects of high performance computing and how it's enabling AI?
I have a lot of thoughts. I'll let Sheila go first.
Okay.
Yeah, so you're asking how the AI is being enabled in high performance computing?
No, my point was that, there are some challenges in developing chips for high performance computing, right? So in terms of that, I'm not talking about the tools. We'll get to the tools also. I mean, but in terms of the challenges in developing the chips for high performance computing themselves, what is it that you are seeing, and where is the world headed to in that regard?
So yeah, high performance computing also there's two pieces for high performance computing right now. There's a compute accelerators and also AI. That is where, so the accelerator computing is one thing, and AI is actually an added piece onto that, which is complementing each other. And that is where we definitely need a lot of compute cores and high memory bandwidth, like I mentioned before. And this development requires a lot of optimization, and I'm not touching the tool, and I'm talking from the development side, how the challenges and complexities are, and we need the best performance. That is the other thing, because AI is quickly, AI is all about learning and then training and reacting, right? So it has learned, it has got a lot of LLMs and natural language models and other database. But when something happens, for example, I can take from a car perspective, self-driving, right? It has got a lot of reference language models as a database. And when car goes on self-driving mode, it has always had to watch the lane and the traffic and everything and quickly react. And that means the latency and performance is a very big issue. So this computing and AI has to go together, and I cannot go in a lot of details of what we are doing right now. And that is becoming a very big challenge from the development side, because we had to have a very latency and performance at the same time getting the least power. And that is where a high computing complex chip we are struggling in the development. And also, it also needs best neural processor to make sure that we have all these languages and we can really refer and train for the next actions or reactions. Those parallel processing, that's where a lot of parallel processing is required. And when you say CPUs can be pipeline computing and AI need to be a lot of parallel processing. And this has to go hand in hand. And that is where the complexity of making sure the verification and validation is done. And we are not erroneously making any decision which would cost, especially for a car and something, right? And also we have some fail safe. Those are things we are considering from an automotive SoC. But then high performance computing, Rajesh can actually touch base on what is required.
Yeah, I think that's great set of insights. I'll probably complement with this, market insights, because everybody's trying to predict where we are going to go next, right? The crystal ball, your guess is probably good as mine. One of the insightful interview that I recently heard about was Sam Altman, right, of OpenAI. He talked about how compute is going to be the next currency, right? Right now, everybody's focused on building the models and stuff, but compute will be the next currency. And you can see a lot of these big tech companies gobbling up the cloud hardware, right? Whoever has the access to the best hardware develops these models. So the compute is going to be the currency of the future, and you can see, you see that semiconductor war shaping up. And for us being in semiconductor, it's a great time to be, right? So, and if the question is, how do we think it's evolving? To me, it's very essential from a market standpoint that the access needs to be democratized, right? What do I mean by that? For example, right now, there's a lot of focus on running these models on the cloud. A lot of players, providing different kind of accelerators in the cloud that Sheila was saying. There are CPU compute, there's a GPU compute, right? There is an emerging, domain-specific accelerator compute. But most of the compute right now, especially the AI compute, which is exponentially increasing, is happening in the cloud. Cloud is great, right? There will be, it will drive a lot of robustness. But going forward, I do think there needs to be a very healthy mix and match about a hybrid model, right? There are models and some of your workload, which is great to run on the cloud, high compute. But you have most of the devices around you. You have your smartphone, you have your laptop, which you always have with you, right? Those are also getting packed with a lot of really power efficient compute, right? They could be used to run some of these models locally. I do think the future is this hybrid architecture where the models could be seamlessly run across cloud and the edge to give the end user the best benefit, right? If the user wants privacy or is not comfortable sharing their data to the cloud, but wants to get the best AI features, maybe there is a client on the low edge where it runs. Cloud is more robust. I think that's an interesting tussle and improvement that I'm closely tracking.
Interesting. So moving on from the AI application to how AI is being used in the development process itself, for example, the SoC development to improve efficiency. Sheila, any thoughts on that? What are you seeing, and what are you seeing as the future of AI being used for the development itself?
So yeah, that's a good question. And like Rakesh was telling, like associate designs are very complex, especially with now a lot of compute, AI engine, and high-speed interface, with large size memory cache and high memory bandwidth. All this adds to the complexity. And at the same time, TCO, total cost of ownership, and bill of material is the decision factor. What does that mean? Means these chips has to be optimized for the best PPA, but at the same time, the time to market is also very key. So, like I said, when I started the development, chip development, the team, GM for that group was addressing us as a new college grads, and he said silicon is very expensive, and as now it becomes a more and more reality, and it really struck with me because of the cost of the advanced node fab and of wafer pricing and the cost of the development. So what does that mean? Means we cannot afford to keep on spinning the multiple spins of the chip, and chip development has to be done with an intention of correct by construction and also first time right. And that is where Gen AI-based tools plays an important role, where it can get help the productivity and also to get a better product. And Anirudh, the CEO of Cadence, was telling in one of the keynote that Gen AI is an icing, like an icing on the cake. We have this Gen AI flow should work with all the inherent or underneath the tools and flows to get the best product juice out of that particular with the Gen AI based AI tools. And with what the need of PPA optimization means, the designers want to explore multi-dimensional options. And this with this infinite compute or infinite EDA tools alone will not cut. And that is where EDA, Gen AI-based EDA tools plays an important role. And this accelerated computing, and the cloud-based accelerated computing and Gen AI together is transforming the EDA tool and how the designers are going to use this to optimize the design. And Gen AI-based tool is all over there now. You can generate a code from the spec. It is used in synthesis. It is used in verification. It's also used in the backend PPA optimization. But if I ask me, I think Gen AI-based simulation tool for verification is playing an important role because, as you know, verification is one of in the silicon, which is never time to do everything because of the vast amount of use cases and scenarios and coverage. Getting a possible coverage is really an impossible task. And also, it is very difficult to ask me what is done meaning of verification. It's hard to say because you always find another bug. That is why. So that is where Gen AI plays a role. You can cut the regression test suite, so you can run more and more regression, and also you can uncover coverage holes, predict the cousin bugs. Like if you found one bug, and there could be a bug associated with that, which may not be seen till you fix a code. But then we can say, okay, this bug may have an inherent bug in another place. Please have a look at it. And also you can predict the risk. That is very important, and that is improving the productivity. And also there are a lot of case studies which Gen AI-based physical design was used to optimize the PPA. And like Rakesh was telling, a small milliwatt of power in the chip will help to reduce the power consumption of the grid, as these chips are shipped trillion times in their life cycle. So at the end of the day, Gen AI-based EDA tool is not only improving the productivity, it's also helping to create a better product.
Very interesting. So from enabling AI to using AI for its own purpose, that's an interesting journey. Thanks for those insights, Sheila. Something on memory technologies, Rakesh. So, what role does memory and some of these newer architectures that that are coming up, like the MRAM, the 3D NAND, what kind of role do they play for the different evolving AI use cases overall?
Yeah, I mean, I'm no memory expert, but I deal with a lot of these workload analysis when I ask my engineers, hey, move the heaven for me because I want this use case, right? Typical characteristics, right? There's something like LLMs you talk about, right? They are, along with being compute bound, they are extremely bandwidth bound, because to generate in every word, you need to transfer data from the memory to the processor, and it's predicting each word as it goes on. So these are very heavily memory intensive applications, right? That's why you will see in some of these data center kind of chips, there's a lot of focus on high bandwidth memory, HBMs, right? And there's a lot of innovation going on the interconnects, right? How can we make the logic and the data exchange faster, right? What are the different interfaces that needs to be used? Depending upon cloud or client, there are different solutions like Ethernets, high-link ports. So for LLMs, along with compute, I would argue that memory is going to be the key. So one of the trends, right, without going into the depth of this technology, is there's been a lot of research on, hey, how can we split some of these compute? Right? How do you splice and dice the problem? You can either make the interconnect going between the core logic and the memory faster, right? And some of the advances there we talked about, chiplet technologies. Photonics is another interesting technology where you're trying to increase the speed at which the memory and the core logic can exchange data. The second one is which is interesting, it would be is how do you split some of these compute, right? There is this concept about PIM kind of a memory modules where the memory can have some integrated compute so that it can do some pre-processing before it actually sends the data out to bandwidth is going to be reduced. So I think this is going to be a very interesting challenge for the industry to solve. And I know memory vendors are actively looking into a lot of these different exciting technologies.
Interesting. Staying with you, Rakesh. Go
I
ahead.
want to add
Yeah.
one thing about MRAM. You were talking, just commenting about MRAM. MRAM is actually, since I worked in Intel and also in automotive industry right now, MRAM is becoming a big integral part or influencing both the defense and automotive industry a big time because of the density and the latency. And that is where MRAM is going to play a big role. It is shaping up. Most TSMC and also Intel Foundry is trying to get MRAM in their technology nodes and also qualified. And now there are automotive chips are coming out with integrated MRAM, because that will help to load a portion of the Linux or something as like a flash, and then download to the chip as soon as possible because of the latency or a quick startup required for example, for a car. You cannot wait for seconds, right? You have to wait a millisecond. You need to be able to do some actions in the vehicle. So that is where MRAM is trying to play. It's the same case with the defense. That's what I've heard. So that is where most of the place MRAM is going to play a vital role.
Interesting. So Rakesh, you've had some experience on edge computing and cloud computing, and both are compelling use cases. But given the difference that we have in the computational power, what challenges arise when you're scaling an edge AI solution to handle these complex tasks? And how can some of these semiconductor advancements address these limitations?
Yeah, it's a different design envelope to start with, right? The primary one being the form factor devices, which translates to power efficiency, right? When we talk about edge, we are talking about like, let's say a smart sensor, which is just sitting in your phone, all the way up to like an edge server or a very powerful workstation laptop, right? If you see, even in edge, there is a wide gamut, but one of the primary difference when you're actually designing for the edge is, the power efficiency, right? You have some leeway when it comes into the cloud. Power is obviously important in the cloud, but it becomes extremely more important in the edge, which is per watt. The design envelope is a lot more tighter, right? And that waterfalls into a lot of different other constraints as well, right? For example, memory, right? The memory that you have attached in your laptop or even a small device in the order of few gigabytes, or in a very small device, you still have some megabytes only that you can store. Then a lot of these compression techniques about, it's not, power efficiency applies to everything, right? Beyond power efficiency, how do you optimize what compression technologies that you can use to reduce the memory footprint becomes extremely important, right? And then, heterocompute. I'm not saying heterocompute is not important in the cloud, but heterocompute also becomes a lot more important in the edge. For example, when you have a very small sensor, a microcontroller is good enough, right? Choosing the most power efficient, just a microcontroller is fine, right? And when you go to the other end spectrum of the edge, you need to choose your CPUs, your GPUs, right? You are picky about what the industry now calls as an NPU, or a neural processing unit, delivering these power efficiency. So the design envelope itself is different, and edge is very, very fragmented because you have n number of different devices. So the fragmentation also causes a lot of heartburn when you're trying to design as a company to get to take over this market.
Interesting. I think we are heading towards the end of the session, but there was this one question on nanotechnology and material sciences. Any of you, Sheila or Rakesh, do you have any thoughts around innovations around the nanotechnology and material sciences space, which are improving the power efficiency and performance of devices? There is this question from Pinku Singh that has just come up.
I'm not the person to answer that question.
Okay.
Yeah, I'm not a nanotechnology expert, but if I elongate that question, there is a lot of research going on in the material science, right? Silicon has been around for a very long time for the obvious material properties that it brings in, right? There's been a lot of research going on in gallium arsenide, silicon carbide. What are the different kind of material technologies that comprehends are going to benefit from silicon, right? Even the photonics is a different, very, very interesting concept, but that stresses what kind of material needs to be used. One of the challenges that I have seen or observed, again, I'm not a material science expert, is having these production at high volume. Sheila touched on this, right? Yield becomes a very, very critical aspect because you're trying to ship millions and billions of this, right? That is where some of these new innovative technologies, which might have proven themselves really good in a specific use case, struggle when we try to reach mass production because the supporting back-end technology might not be there, or we don't know much about the material itself.
Okay. Yep. Thanks for that. So the last question that I wanted to touch upon in this session was on the whole energy efficiency and sustainability topic, right? That's the concern, especially given that we are seeing on the AI front this huge amount of compute resources that require, and hence, more power. What is the industry thinking about this, Rakesh? First, we'll start with you and then go to Sheila for her remarks on this topic.
Yeah, I mean, sustainability is a very, very important piece. And to me, it is multifaceted, right? As you pointed out, when we are making our own solutions, products, chips and processor more energy efficient, less energy is required to cool it. For a customer, there is a better TCO. And for the environment, it's better because you're spending less resources to cool your electronics, be it data center, be it even your laptop or whatever, because you're consuming less electricity, right? So from that sustainability angle, designing for extremely low power, using the right materials in the packaging and stuff is going to be important, right? When it goes to the end product, I do think that is where I think an equal, if not greater, impact can be created, right? When I work with our OEMs, there is a lot of focus on when you're building a laptop, you're building a smartphone, right? How do you design it for repairability, right? So that when your favorite device goes bust, you're just not dumping it in the junkyard, but you have an option to replace components or extending the shelf life. So there's a lot of focus on repairability when it comes to different countries. They have their own laws and regulations, right? And also using sustainable materials. A lot of these electronic devices pride themselves in using recyclable materials into consumer electronics, so it's good for the consumer. And the struggle is the education piece, right? You need to educate the end consumer that this is important, right? Either if a device charges premium because it's using recyclable material, can that translate into a consumer buying process? So there is definitely a consumer education piece that is ongoing as well.
Interesting. Sheila, any thoughts from you on sustainability and energy efficiency?
Yeah, I can talk from what countermeasures we are taking. Basically, like power is a big concern, and we are taking a lot of measures to counter it during the design phase. And like Rakesh was telling, dollars per watt is becoming a big ticket item in TCOs these days. GenAI-based ADA tools are helping, flows and methodologies are helping to optimize the power as much as possible. And I touch base on how much a small amount of power reduction in a chip can save a lot of power consumption in the grid. But then how we go about it, that is where it is, right? We need to have a design spec with a detailed power requirement. You need to have a low power design methodology. We should have power islands and power domains, and also we should be able to shut out the part of the chip which is not active temporarily. And also these chips have many, many cores, and not all the cores are active always. We should be able to shut off the cores which are not active again temporarily. So that means we need to have dynamic voltage and frequency scaling, power gating, clock gating are the other techniques which we use in the design to optimize the power. What does that mean is you need a lot of verification and validation to make sure there is no data loss or data corruption, and it is not operating erroneously when it is coming back to active. And that is where we had to take extra measures, and a UPF-based design flow has helped in order to verify both in the verification side and the backend side to make sure that these power saving measures have been implemented properly and it works as intended. That is the main thing. It need to be working as per as intended in the spec. And also another measure we take is more the software codes, which doesn't need large performance compute to perform some of the low performance code, right? So we move those kind of software codes in low performance CPU, which mainly can be used or which consumes very less power. And this is from the design methodology and application perspective. That is where we take some of the power saving measures.
Interesting. Well, on that note, I think we have just about run out of time, but thanks a lot for these wonderful insights and weaving in some very practical aspects of, things from your own experience into this whole conversation. Much appreciated, Sheila and Rakesh. Thanks a lot for your insights on this topic. And that's where I conclude and hand it over to Nitin again. Nitin.
Thank you, Vivek. We extend our gratitude from AICO Sports side to you for the excellent moderation of today's session. And a big thanks goes to our speakers, Rakesh and Sheila, for your insightful contributions to this discussion on the semiconductor industry. I'm confident that all the attendees who attended today live as well as through our platform would have found it to be both engaging and enlightening. As we wrap up this conversation, I would like to take a moment to recognize and thank our community partners, speakers, and attendees for their ongoing support and participation over the past few years. Your involvement has played a crucial role in creating an environment conducive to knowledge sharing and enrichment. The insights shared by our panel members were truly exceptional, and we appreciate their collaborative spirit and expertise. For those who may have missed any part of today's session or want to revisit it again, the recording will be available on our company's YouTube page for your convenience. Looking ahead, we are excited about the promising technological advancements that lies ahead in the coming months. So keep connected with us. At AI Core Spot, we have a diverse lineup of events planned across various sectors every month, which includes banking, financial insurance, telecom, retail, supply chain, manufacturing, healthcare, and so on. We encourage you to stay connected with us for ongoing learning opportunities and updates on the latest technological developments. You can find a wealth of knowledge, including detailed announcement events, registration assistance, which is there in our website and all the social media channels which we have. Your support is invaluable to us, so please consider liking and sharing our content within your network. A special mention to InfoVision, who is our esteemed knowledge and innovation partner, and Digit7, who is our technology partner, for their unwavering support and collaboration. Be sure to explore their websites to dive deeper into the world of technological advancements. We thoroughly enjoyed hosting this session and hope you found it as enriching as we did. We look forward to continuing our journey together and bringing you more insightful sessions from different topics in the near future. Until then, take care. Thank you once again for all of your participation and support. Have a great day and nice week ahead. Bye. Take care.
Thank you.
Thank you.
Thanks, everyone.